Welcome back, everyone, to the second installment of our Introduction to Counting and Probability video series, in which we'll mainly continue our discussion on independent events.
If you remember from last week, we assigned you two problems to solve, which we will discuss. We have provided a solution for the first challenge problem in the PDF file in the video description, since the second problem is the most relevant to today's topic.
In case you did not solve the problem yet, please take the opportunity to do it now, as we will present the solution next. Notice that for each choice of delegate that Mercury has, there is no correlation to the choice of delegate chosen by Venus. This also applies to Mars. Thus, we are working with independent events. Hence, for each of the 8 possible representatives that Mercury can choose, there is 7 possible delegates that Venus can choose and 6 possible delegates that Mars can send, meaning that there's 8 times 7 times 6, or 336 total combinations of delegates, 3 distinct combinations of delegates the 3 planets can collectively send.
Before we continue, we need to clear up some terminology, specifically the definition of a factorial. To do this, we will try to solve an example problem. And here's the problem. James has 7 distinct books on a bookshelf. How many possible distinct orderings of the 7 books can he perform?
This problem isn't actually very different from the previous one we reviewed. Once again, try to solve this problem by yourself before we reveal the solution.
We will assume that James starts off with the first book available to him. We know that there's 7 possible spots for him to place this book.
For the next book, there's only 6 possible spots available to him, since one of the spots was taken by the first book. This continues with 5 spots left for the third book, and so on.
Hence, the answer is 7 times 6 times 5 all the way to times 1, which simplifies to 5,040.
We can generalize this to n books. If James has n books, there is n times n minus 1 times n minus 2, all the way till 1 ways to arrange them. This generalization translates to the definition of n factorial, abbreviated as n with an exclamation mark at the end.
Do not memorize the definition of n factorial as n times n minus 1 all the way to times 1. Instead, learn about what it actually represents.
The next 2 challenge problems for you to solve are much more difficult than last week's problems. Thus, we'll give you a hint to guide your progress on them, and here is the problem.
The idea of not memorizing, but instead fully understanding a problem-solving method will come in handy for today's problems. Make sure to solve these problems now, as we will use their general essence for our next topic.
So here's the hint. If an individual has y repeating objects out of a collection of x total objects, such that the remaining x minus y objects are distinct, first calculate the number of ways in which the repeating objects are treated as distinct. We will now present the solution to problem 1. Your first intuition may be that there's 7 factorial total ways for James to arrange his books. However, we will investigate why this is incorrect.
We will take 2 specific cases. If the 5 distinct books are A, B, C, D, E, and the non-distinct books are both F, then our current intuition states that the following 2 arrangements are distinct, even though they are obviously not F, F, A, B, C, D, E, and F, F, A, B, C, D, E.
This occurs since for each of the 2 factorial arrangements of the F's, we treat them as distinct. Hence, we divide 7 factorial by 2, giving us 2,520 as our answer. This process is known as accounting for overcounting and is a fundamental counting technique, so please make sure to fully comprehend this idea.
Our next topic is committee forming, which builds on the idea of avoiding overcounting.
We will explore this idea by solving the following problem. How many ways are there for a group of 4 people to build a committee composed of 2 people? Pause the video and solve the problem.
We begin by noticing that both positions of the committee are indistinct. This means that if the chosen committee members are A and B, then AB is not distinct from BA.
From the challenge problem from last week we reviewed, we find that there's 4 times 3, or 12, total ways to form the committee if the 2 positions are indistinct.
However, we have divided by 2 factorial, as the 2 committees' positions are identical. Hence, the answer is 12 divided by 2 is 6.
A very similar method applies if we were to choose 3 members to form the committee. We simply compute 4 times 3 times 2, but divide by 3 factorial, since the 3 positions are indistinct. We could also find the number of ways to exclude a single person from the committee, which is trivially 4.
It's time to introduce new terminology, which we feel that you're ready.
We're going to introduce you to the n_choose_k function, which is pronounced, of course, n_choose_k, where n and k are variables that represent the numbers. n_choose_k is the number of ways to choose k indistinct objects from n total objects.
Try to develop a general formula to derive n_choose_k with the description we just gave. We will present the formula next, so please have your guess ready. n_choose_k is equal to n factorial divided by n minus k factorial times k factorial.
n factorial over n minus k factorial describes the number of ways to choose k distinct objects from n total objects. We divide the above expression by k factorial, since the k chosen objects are indistinct.
I think that we've reached a good stopping point for today. Do not memorize the formula for n_choose_k. Understand where it comes from.
Here's today's challenge problems for you to solve, and make sure to have the solution ready for the next video. And please subscribe to our YouTube channel to receive notifications on when we release our next videos.
Yeah, subscribe and hit the bell while you're at it. Also like it to see